Nuclear medicine is the branch of medicine that uses radiation to provide information, and that information is about the functioning of a person's specific organs. So X-rays providing us with a picture of the anatomy of the bones. The nuclear medicine provides us with how the organs function. Some of the organs we can look at include thyroid gland, which you can see here. It's difficult to see. We've got the spine around there behind it, the trachea and other parts in the body. We've got here the liver, the gallbladder, and parts of the rest of the digestive system that could be looked at. We've also got a PET scan of the lung and heart that we can look at. Here you can see a cancer has appeared on the screen, and we'll explain that a little bit later. So that's a PET scan. We've also got here another PET scan of the heart, showing areas that appear to have more activity or that have more of the radioisotope that we'll talk about taken into them. All of those organs can be easily imaged, and disorders and functions can be revealed or measured much more easily than in, say, an X-ray, which is basically, except for a CAT scan, that's some exception, but the X-ray is a little more to do with the anatomy, the structure, whereas the medicine imaging, such as isotopes, PET scans, have much more to do with the functioning of organs, not their structure. Okay, so this type of imaging using radioisotopes, another term for that is radiopharmaceuticals. The diagnostic side of nuclear medicine, which requires a well-trained, educated people, doctors, diagnosticians and technicians to be able to look at images that were created and then provide information for doctors and specialists to make a diagnosis. The diagnosis is basically just looking at symptoms and imaging, and then coming up with the identification of the nature of the illness. So what is the disease or the problem that the person is having? The other side of nuclear medicine, in some cases, it's used as a treatment. So we have the diagnostic side, where imaging, doctors, nurses, people that are trained look at the images that are created using nuclear medicine or radiopharmaceuticals. And the other side is this treatment side, where radiation can be used in some cases to kill or destroy or treat diseased organs. And that is often called radiotherapy, and it's used often to cure or to try and cure or stop cancerous growths or irradiate tumours, prevent a person from dying from those particular diseases. Can also be used in areas such as arthritic problems. There are many different techniques that can be used when diagnosing people. One of them uses radioactive tracers, and these usually emit gamma rays from the body, and they can be captured or recorded by a gamma camera. A camera that uses photons of gamma rays rather than light. So a normal digital camera would use light photons to expose a digital sensor. The gamma camera detects photons of gamma rays, and it's a little bit different, and we'll see that in a moment. A tracer is a radiopharmaceutical or a radioisotope. It could be an isotope connected to another chemical, another molecule like glucose, or it could be a radioisotope itself that's releasing these gamma rays. And we don't want radioisotopes in the body releasing alpha and beta particles, because if they're continuing to release, they often can be quite destructive and increase the chance of causing damage because they are ionizing. They're also difficult to get out of the body. They don't leave the body, whereas gamma rays produced inside the body can leave the body and be detected by a device. Isotopes have to have a short half-life. Example is technetium-99 metastable, and it has a half-life of about 6.1 hours. It decays into technetium-99, which has a half-life of around 211,000 years, but it's not a high producer, and it produces very small amounts of beta radiation, so small that they are less than the background radiation, which is radiation that we'd normally find outside the human body, around in the environment. Pharmaceuticals could be linked to a molecule such as glucose, and when we look at glucose, this particular one has a radioactive isotope present, and it's there as a tag. So this glucose molecule still acts, and it's actually FDG, or 18 fluoro deoxy glucose, and it's treated by the body as if it was glucose. And here you have another example, the same sort of diagram, and the one that we're interested in is the fluorine 18. That produces positive particles called positrons, not gamma particles. These positrons are basically positive electrons in a sense. The principle behind PET scanning, which we'll look at later. We use these tags such as fluorine 18 in our FDG, glucose molecule, is to allow specific physiological or the chemistry of life processes to be examined. An example of that would be an uptake of glucose by if you have a tumour in the body and normal tissue around it. The tumour, because it's growing faster, is absorbing more water and glucose. It has a higher rate of metabolism, and it's growing faster than the tissues around it. So when we put this radioactive tag, a glucose molecule tagged, into the body, the tumour will take more of it up, and we'll expect to see more of this in here and less out here. And when we then image this, the cancer will produce a hot spot because it has more of the radioactive isotope in it emitting. And in this case, it has positrons, and they're emitting, when they reach an electron, they're emitting gamma rays, which can be detected by the gamma camera. And we'll have a look at the gamma camera next. These radioisotopes can be taken several different ways, or put into the body several different ways. By injection, inhalation, so as a gas, or by oral administration, so eating or drinking. So a gamma camera is a device that's used to take an image of the hotspots or the areas where there's radiopharmaceuticals have been absorbed by tissues in the body. So you might use a particular one that in PET scanning is good for looking at the brain. So glucose, because your brain uses so much glucose, it uses a third of your body's food supply. That gamma camera, and we have a picture of one here, takes images. If we have our body here, so a person's head, the body, and we have a concentration of radiopharmaceutical in a particular spot. So maybe a tumour's growing there, and the tumour has taken in extra fluorodeoxyglucose, a tagged glucose molecule, and is giving off gamma rays. Now, the gamma rays, as they pass up, go into this machine, and there's crystalline substances here, sodium iodide, there's photocircuits and photocell. There's a digitizer to convert the information into digital information, and a computer and a screen and an operator, so you'd be able to look at various parts of the brain on a screen attached to that computer. Typical sort of gamma camera, what do they actually look like? So here's an example of one. Patient would lay on the bed and the gamma camera up here at the top. So the patient would be here on the bed. This part of the bed can move in and move the patient under the gamma camera, vice versa. The camera can rotate around, taking different angles of the patient, and basically the hot spot would be giving off gamma rays. It can be traced and recorded in this large gamma camera section here, and that's then sent to an image processing unit, but also then to a screen or recorded media where somebody can make a diagnosis. So it's not up to the technician that's there. Usually they record the information and then it can be sent to a specialist. Here you can see another image of the actual scanning process, and you can see, depending on the radiopharmaceuticals that's used, you've got here on the monitor you can see an image appearing. So the information, and I think it looks like from lungs or something, information is being released in the form of gamma rays by this radiopharmaceutical. This is not PET scanning, a little bit different. It's just detecting the gamma rays being released from the radiopharmaceutical, and they are being detected in this large device, then sent to the computer and then to a monitor where they can be observed or recorded. And here again you see the same thing. If there was something in this part of the body, you would be getting an image from the gamma camera of a hot area or zone where most of the gamma rays are being released from. Now this requires that the radiopharmaceutical has time to be absorbed into either a tumour or bones or whatever you're looking at. In the case of bones, that would be called a bone scan, and the material might be technetium with a phosphate group attached. And bones use phosphate, so that phosphate group will go into the bones, taking the technetium 99M with it as a sort of not a compound, a complex containing the technetium and the phosphate groups. The procedure is pretty much what's used to do a bone scan. Okay, using technetium as a complex with, so that's 99M, with a complex with a phosphate group. They're both absorbed into the bones, and then the bones release, depending on the amount of technetium that's absorbed. Areas with tumours would absorb more of this substance and create hot spots which would reveal themselves on the screen as a brighter area, producing more gamma rays. It also can be used for areas where there's less gamma rays being produced because the bone might be damaged or have issues surrounding that. More recent technology is the PET scan. And the PET scan is basically positron emission tomography. As you saw, tomography is used in the word CAT scan, but it's basically mapping, and it's mapping this positron emission. How do we map positron emission? Well, we use a positron emitting isotope, such as fluorine 18. It produces these positrons, and it's produced in a cyclotron, which we can look at later. They're basically positive electrons, and they're released by these radioisotopes or radiopharmaceuticals that are produced inside a cyclotron. As the substance goes and emits these beta particles, these positive beta particles, they meet up with your normal electrons inside your body. Okay. Normal electrons. Those electrons, when they meet a beta particle, positron, sorry, they annihilate each other, and out comes gamma ray. Actually, two gamma rays, and they come out at 180 degrees to each other. So one in this direction, one in this direction. Now, if you have something around this emission which can detect those gamma rays, it can detect them, and you can trace it back to where that annihilation occurred. So if we have a person's body just a cross section of part of it. Our annihilation occurs here. We have around here a type of gamma camera, which can be rotated or it has enough sensors around it. After that annihilation, the gamma rays go here and here. The computer can then track them back to the point where that happened. And that's more likely to happen where there's more positrons being emitted. Positrons are emitted where there is more radiopharmaceutical or radioisotope. And more of that will occur where the body has taken up more of the radioisotope. So if you've got a tumour that's using more sugar, you might use FDG with 18 fluorine in it. And FDG will produce these positrons in the body. They'll annihilate, and off comes our gamma rays, and they can be detected and then traced back to exactly where that was in the body. So it's a very accurate way of mapping where these annihilations are occurring, where these gamma rays are coming from. If a gamma ray comes out and it doesn't have a corresponding gamma ray on the other side of the device, then we know that that was not emitted by the positron, by the annihilation, because the annihilation always produces two gamma rays. Our PET gamma camera, has to be designed in a way that it can trace back these original annihilations from the detected gamma rays. Those gamma rays are identifiable, as I said, when there's no other gamma ray coming out the other side, then this gamma ray here was not produced by the radiopharmaceutical. These gamma cameras and gamma detecting devices, they give us a good idea of whether there's organs in the body that are malfunctioning. And through careful selection of the radiopharmaceuticals, we can figure out what organ will accumulate more of this pharmaceutical, or what organ won't accumulate more of this pharmaceutical. So if a particular organ is taking up a lot of the pharmaceutical, then it will appear hot, or an area with a lot of gamma rays being produced. If an area is not taking up a lot of this pharmaceutical, it will appear cold, an area where less of these gamma particles are being emitted from. And that could be the organ's not functioning correctly, so it's not taking up what it's supposed to take up, in case of, say, the brain, FDG, or other organs that would need a particular tagged radiopharmaceutical. Over time, if you view these images, then we can work out a pattern. So are the organs functioning correctly over time? Is the rate of uptake by the organ, or the absorption of those isotopes of the organ, is that changing over time? Is it slowing down? Is the organ not working properly? If we have that changing rate of uptake, then we know there's a malfunction in the organ, and we can make a diagnosis. Is there an issue? Is there a tumour? Is the organ failing? Is there, in case of the brain, is it Alzheimer's disease? So we can use these radiopharmaceuticals to take advantage of this functioning issue. X-rays, remember, mainly anatomical. They're not tracing things happening over time. They're not tracing the uptake of materials, and they're more useful for just looking at the anatomy, the position, the structures, whereas these radiopharmaceuticals, PET scanning, and radioactive tracers are much better for looking at the way organs are functioning. Where do they come from? Where do we get radiopharmaceuticals from? In Sydney, it's ANSTO, Australian Nuclear Science Technology Organisation, and they produce molybdenum 99, which decays to make our technetium 99M. This process here delivered to hospitals. This takes, I think it's 36 hours. Actually, it would be more, so it's 67 hours or so to convert into this. That's what's used in our bodies. It has a 6-hour half-life. This is a half-life of much longer, but it's still less than this one. That decays into technetium 99 in our bodies. This technetium 99 has a very long half-life, but it is a weak or soft beta emitter, so it doesn't produce as much in our bodies that will cause us as much of an issue. And the beta particles produced are lower than background radiation. Just recapping, the ANSTO Institute is well within major capital cities. It has transport and is close to hospitals. And that's because this low half-life, hospitals need to have a supply of these substances to use in their scanning. So they have to be close, or they have to be within airport range or transport range. By the way, is at Lucas Heights, which is south of Sydney. And just to recap previous work, you want substances with a short half-life that emit gamma rays, which can be detected outside the body, and that are excreted quickly, or they produce a substance they decay into a substance that will be less harmful. So that's our ideal isotopes. And when you use a radioisotope for scanning, it becomes a radiopharmaceutical. From the word similar, pharmacy.